Welcome back. Picking up where we left off. So far, we have just dealt with atoms when we were interconverting using Avogadro's number and the molar mass. But most of what we're going to deal with in this class and in our lives as well is molecules, not atoms. Now, we do deal with atoms a lot as well, but anything interesting is really going to be made up mostly of molecules. The good news is that everything we've done up to this point can be applied exactly the same way to molecules that we've been doing it with atoms. The only difference is instead of taking just a single molar mass from the periodic table, we would add up all of the molar masses from all of the individual atoms in the table when we are calculating the molar mass of a molecule. So example 6.5, for example, if I pull that up here in my book, it asks us to find what is the mass of 4.78, let me write it down up here, 4.78 times 10 to the 24 molecules of NO2. So we want to know what is the mass of that many molecules, where we are going to be doing the exact same thing that we did in the previous video. We're starting here. Well, I say we're doing exactly the same thing. We're actually going to be doing the reverse, because in the previous video we started here with the mass and went backwards. Now we're going to start with the number of molecules and go this direction. So we're going to use Avogadro's number to convert that number of that number of molecules into moles, and then we'll use the molar mass of NO2 to find the mass. So let's go ahead and do that, and I think I should have enough space down here. I really should have made an extra slide here for me to do that in, but oh well. So we have 4.78, and I'm going to put E24, so the E stands for times 10 raised to the 24th. So that is that many molecules. The first thing I'm going to do is I'm going to use Avogadro's number to convert that into moles. So I know that I will have 6.022 times 10 to the 23rd, in this case molecules, for every 1 mole. So my molecules here cancel out, leaving me with moles. So that is this first step. I used Avogadro's number to go from molecules to moles. The next step uses the molar mass. Now NO2 has a single nitrogen, which is 14.01, and then 2 oxygens, which are both essentially 16. They're technically 15.9996, I think. Or maybe it's 8. But anyway, it's essentially 16. And so that is going to end up giving us 36, I think, but I don't trust myself to do that in my head, so I'm going to plug it into my calculator real quick. I've burned myself before, so, well, 56.01. That's what I think it would be. Or sorry, yeah, 46, not 56. 46.01. Okay. So we have 46.01 grams per mole. And again, these numbers, the 14.01 and the 16, they just come directly from the periodic table. So this is the number for nitrogen. This is the number for oxygen. We have 2 oxygens, so I multiplied the number for oxygen by 2. And that gave me the 46.01. Okay. So then, for every 1 mole of NO2, I will have 46.01 grams of NO2. So that if I do all that math, 4.78 times 10 to the 24 divided by 6.022 times 10 to the 23rd times 46.01. That gives me 365. Let's see, I'll only get 3 sig figs, so 365 grams of NO2. One for each day of the year, except for this year, because this year is not only a leap year, but it is also interminable. So, if you're watching this video not in 2020, how are things doing out there? Doing any better? I hope so. Moving on. Let's talk about chemical formulas as conversion factors. So, we're kind of used to doing things like this without even really thinking of them, but let's stop and think about this for a second. If we have an object, and the object is made up of parts, it's often useful to think about the ratios between parts for whatever it is that we're looking at. So, for example, one of the definitions of a spider is a creature that has 8 legs. It's not the entire definition, but that is part of the definition of a spider. So you can say that for every one spider, you have 8 legs, unless you have a spider that's had a really rough life. You're going to have 8 legs for every one spider. In the same way that you're going to have 4 legs for every one chair, or 3 leaves for every clover, unless you get super lucky and find a 4-leaf one, which I have never done. And I spent a good bit of time looking for one when I was a kid. Don't ask me why. I don't know why. But I distinctly remember spending hours looking through fields of clovers for a 4-leaf clover. Never found one. Maybe that explains some things. Anyway, moving on. We can do the same thing with molecules here. So water, as an example, we can set up a ratio between molecules of water and the atoms inside of that molecule. For example, there are 2 hydrogen atoms for every 1 water molecule. It's a 2-to-1 ratio. And that is inherent in the H2O. It tells you have 2 hydrogen atoms for every molecule. We can do the same type of thing with any molecule that we come across. So, carbon dioxide, for example. If we know how many moles of carbon dioxide we have in a sample, we can use the inherent relationships between the numbers of atoms in the molecule to work out how many moles of oxygen we would have. In the case of CO2, it is a 2-to-1 ratio. For every mole of CO2, you will have 2 moles of oxygen. In the same way that for every dozen people, you will have 24 arms. Again, assuming that you don't have someone that's had a very rough life and lost one for one reason or another. On average, for every dozen people, you're going to have 24 arms. In the same way here, for every mole of CO2, we will have 2 moles of oxygen, because there's a 2-to-1 ratio there. And so we can apply this to any number of moles of CO2. So as you can see here in this example, if we have 18 moles of CO2, we just apply the ratio that is inherent in the molecule itself, and that tells us that we would also have 36 moles of oxygen. Just 2 times however many moles of CO2 we have, that's how many moles of oxygen we would have in that same sample. So another example here, example 6.6 asks us to determine the number of moles of oxygen in 1.7 moles of calcium carbonate. Well, if we have 1.7 moles of CaCO3, actually, why don't you give this a try? Pause the video for a second here and try to work out how many moles of oxygen we would have in 1.7 moles of calcium carbonate. Okay, I hope you paused the video there and you were able to work out that this is a 3-to-1 ratio. For every 1 mole of calcium carbonate, we have 3 moles of oxygen. And again, that is just from the molecule itself, from the chemical formula, is a 3-to-1 ratio. So then, if we have 1.7 moles of the calcium carbonate, that means we must have 5.1 moles of oxygen. And I hope that's what you got when you worked that out. So let's take that one step further here. And, well, actually, I think I'll save this for the next video because it ties in pretty nicely to the percent composition or percent mass, which we talked about in the lab. So I think I'll save this for next time. We'll call it there for this video. In the next video, we will take what we just did one step further and apply the ratios not just to converting from 1 mole to another, but then tack onto each end a gram to mole conversion. So we can work out if we have a certain mass of one thing, what would be the mass of something else in that same molecule. So I'll see you in the next video.